then you have infiltration, and then you have computer, how much energy comes from the computer, and you have to keep track, because sometimes the building there are two people, sometimes there's one people, sometimes you would like to put the computer on and off, depend on what you have to do. Okay, therefore, and then we mentioned these are the temperature for outdoor. And what else you need, sir? What do you need now, sir?
It's the equation balance between the person, the hair from the conduction hair from the walls, and the computer and
Okay.
the
Here, that when you're writing the energy balance for room air, this TI, okay, you have convection from this one to this one. It means H times the area of the east wall, T4 minus TI, plus H times the area of north wall times, I don't know what number it is, your case, minus TI, plus convective heat transfer from the west wall, H times A area of this wall, times the T and 8, 9, I do not know, plus for the south wall, and you have two more, one from the floor, one from the ceiling. Therefore, you have 6 surfaces, you have 6 convective heat transfer to that one. Therefore, this temperature minus this temperature minus this temperature minus this, and so on. Plus, you have an equation that's referring to your infiltration. Again, infiltration is, you can write MC Ti minus T1, okay? Therefore, here you're representing this energy that you're writing, okay? You're seeing one slide or you're seeing many slides? Are you seeing one slide?
Just one slide, sir.
Okay. Good. Therefore, you're writing this one minus this one, okay? Therefore, that's represent your times M, the mass flow rate. Mass flow rate you can calculate because you have the volume of the room and you have air exchange, times CP and so on. Plus, the energy comes from people. Again, you can use a number 65 watts, you can use 70 watts, depending on level of activity that you would like to consider, okay? Again, keep track of time, because sometimes you have 2 people, sometimes you have 1 person, sometimes you have no person. Plus the energy from the computer. Again, you can look at your computer to see how much, what energy has, you can add this one. Therefore, this is the energy for room air. Did I answer your question, sir?
Yes, thank you.
No problem. Let me just, if you need any more explanation, okay, sir? This is last call.
The the temperature inside, when I run my code, it gives me something close to 0. Does it make sense, or
absolutely
should I?
Not. Absolutely not, because you have people inside and you have some infiltration, so on. Therefore, the temperature has to be minimum outdoor temperature, minimum, but it has to be more than that. Therefore, check your equation, the coefficient that you're using, because we'll end up, I don't know how many equations that you have. How many nodes that you have?
I have 18.
Okay, 18. You have 18 equation and 18 unknown. And make sure those variable that you know, you take it to the right-hand side. Remember, you have a matrix. A is the coefficient that you have. And
I just have to go over all the math.
Yeah, you
matrix.
have, when you have, for example, TO is non-value, you take it to the right-hand side. These are the number, positive number, you have to take it to the right-hand side. Therefore, all of the temperature should be above at least minimum temperature that outdoor you have. Minimum you have -5, therefore definitely this number should be much higher than that value. Cannot be 0.
Sir?
Yes, yeah.
I get around like TI about 41 degrees at the maximum. Is that reasonable considering the radiation and people inside?
Yeah, absolutely. Any number makes sense, okay? But just you use your judgment at the end. Mention, for example, during the day, how much heat is enter the room. Okay, that you mentioned computer and so on. And that based on that one, you get an order of magnitude, okay? 41 probably makes sense, absolutely.
Okay. Okay. Thank you.
Sure. Again, remember how much you add energy for the room from the occupant, how much energy from the computer you have, and you can make an assumption this guy is making coffee, therefore there's a coffee machine over there, and that's all, okay? Therefore, make on the assumption, again, use your judgment and look at the number, it makes sense through the wall and the room temperature and outside.
Okay. Thank you.
No problem. Okay, let me go continue.
Sir,
Yeah.
I'm sorry, can I ask a question?
Please do that.
For the floor equation, for the energy balance equation for the floor,
Yes, yeah.
it should be the convection and also the solar radiation that comes from the windows.
Absolutely.
But the Qs that we have are the whole wall should be multiplied by the area of the window to get the
No.
no.
When you write the energy balance for here, for this floor, assume this is your floor. Assume this is
Yeah.
your floor, right? Therefore, you have conduction coming to the soil, okay? This should come to the soil. And then then you have convective heat transfer between the floor and the room air. And then you receive some energy come from the window. How much energy comes depend on the area of the window and the Q it's coming to the window. Therefore, become Q times the area of the window, because that's the amount of radiation comes in.
Yeah, that's what I was saying. Yeah, okay, so Q times the area of the window and times the transmissivity and the absorption. Okay. Okay.
Sure.
Yeah.
No,
thank you.
No problem. Okay, let me go start the lecture. We have, I believe, I don't know, we were chapter 3, right? Yes, let's go here to see what will happen. Either is familiar to you or not. We were here. We did start to this problem. Again, read the problem. I believe we did it almost halfway, almost on the end. We mentioned we have a fin. The base temperature is 350. Therefore, this is the base. The temperature is 150 right here. And then we have convecting to the outside. The temperature of the air in the room is 25, and heat transfer is this one. And the conductivity of material, heat transfer coefficient, everything has been given. Mention determine the efficiency, heat transfer rate. Therefore, we are asked to calculate efficiency, heat transfer rate, and effectiveness of fin. He is asking us to use two techniques. One is based on the table 3.3, and the second one is based on figure 3.43. And last lecture, we show you the first part. We mentioned, do we have the information about the fin and so on? And we mentioned this is the table 3.3 if you have reached that past. Therefore, it's forcing us to use this equation that we have efficiency defined, okay? Efficiency defined as this expression. Therefore, we can calculate the M because we know H, we know K, we know P, we know area. Therefore, M is known, and LC is defined. Again, LC is defined based on this equation. We mentioned this is the thickness. Therefore, is assuming this fin is insulated. Therefore, this is the equation for LC. And therefore, if you look at this part, we have M, we have LC, and we place it here and we calculate. And that's exactly, we did it, and you have it. And from here, we calculate M, and then we calculate LC. LC again is length plus half of the thickness on the top, half of the thickness on the bottom. And area of the fin, we know the size, therefore we calculate, and this is the fin efficiency. Okay, therefore this is the fin efficiency we have been able to calculate. And then we go to calculate how much energy passed. Since we know the efficiency is defined, the ratio of the heat transfer by fin divided by the maximum energy. Therefore, we can we know this information because we know the H, we know the area of the fin, and we know the temperature between the base and environment. Therefore, that is based on the maximum heat transfer that we can have. But we have efficiency of 80%. We multiply by 80% to calculate how much energy is transferred from the fin to the environment. And this last part, it mentioned to calculate the effectiveness, the efficiency, effectiveness definition of effectiveness is cube fin by this one, okay? Therefore, we already calculated the value of this based on the previous calculation, and this is the maximum heat transfer, therefore we have been able to calculate here. Therefore, the effectiveness of the fin is around 17%. Okay, that the effectiveness. Okay. Now the second part of the problem mentioned, go and use the figure 3.43. If you look at your textbook, this shows the effectiveness of the fin. Look at here is fin efficiency, and here is a parameter here. Therefore, this table provides us a sort of a solution to those problems. Therefore, this is the fin we are trying to solve the problem. We know the thickness, we know the width, we know this one, and here. Therefore, we can calculate this value from here, go up, and then from here we go and find the fin efficiency. Okay? Therefore, this graph is also a solution to the problem. Therefore, you don't have to go and do the calculation. This has been done here, and they give you the value. Because we know LC, we know H, we know K, we know the area of the fin. Therefore, this value is known. We come here, whatever is value epsilon, we go up and select this curve here, because this curve related to this geometry of the fin. And if you go up here, we can find out the fin efficiency. Okay? Therefore, if you go back here and we calculate, we can see LC, we have the value. We calculate this value. This was point here. We use figure 3 and we find fin efficiency is 81%. It's almost the same number we got from the previous one. Okay. Therefore, in your textbook, hopefully one day reach those pages, you can see they gave you some equation that you can use some equation if you are doing calculation by hand. And if you're designing and you don't have time, there is some graphs that give you some information how to calculate from the graph without doing any calculation. Any question, please? Okay, therefore, here is the end of the story, my friend. It means we almost finish this chapter. I don't know how far you are, but this is the place I am. Therefore, the idea here is, by now, we finish chapter 2 and 3. By now, the minimum knowledge that we expect that you have here is to understand the concept of thermal resistance and its limitation and develop thermal resistant network for practical heat problem. You have done it. Solve study conduction problem that involved multi-layer, rectangular, cylindrical, and so on. Therefore, some of them we do it in the lecture, some of them that you will see it in assignment that you have. Okay, therefore maybe in your assignment we did it for rectangular geometry and we did it for cylindrical. Probably you have some example 1 or 2 in the assignment. Therefore, make sure that you do it, and I'm going to excuse me, I'm going to send you the solution for the chapter 1 and chapter 2 by tomorrow. Therefore, please don't look at the solution, read the textbook, try to do 1 or 2 problems, and then if you have a difficulty, try to look at the solution. Therefore, start to develop self-confidence that you know the information. Also, from now on, start where you can have during the exam or during the tutorial or during the quiz or midterm 4 pages of equation. It means 2 single page, back and forth, okay? Therefore, whatever equation that you think you need, you can write it down on those pages. If something is needed extra, I will provide you during the exam. But at least I want to encourage you, do not memorize the equation. Just try to understand it. We provide you the equation, but you understand the limitation of the equation. When you can use that equation, when it makes sense. Sometimes you cannot use a certain equation. For example, if the conductivity is variable, you cannot take the K out of that bracket, okay? And identify application in which insulation may actually increase heat transfer. We show you through the one example that yes, there is a limitation for the wall. If you add more insulation, you can increase the resistance, because resistance defines X over K. If you increase X, it means you're increasing resistance, because the area is remain constant all the way. But we notice in the case of cylindrical system, the K value is constant, but the area is changing. The area has changed. Probably you there's an optimum value for the value of the insulation. If you increase more, probably you will increase heat losses. Probably the same thing will be applied to a cylindrical coordinate. Therefore, try to understand the equation, because if you understand the equation, you can also guess the answer. Now the last lecture and this lecture we devoted to fin, okay? Fin surfaces and assess how efficiently and effectively fin we can infuse. In case, as I mentioned, sometimes we would like to reduce the energy by as much as possible by conduction. And the only way to reduce it by adding insulation, okay? But some cases, some applications, we would like to encourage to heat loss. In order to heat loss, therefore we use fin. Again, the reason, because at the end, you have to lose the heat loss to outside the environment, and that's by convection. And when it's by convection, there's a temperature difference that you cannot do anything with it. The only two variables remain is H and A. If you would like to increase H, it means you have to increase air movement. Therefore, you have to use a bigger pump, you have to use a bigger fan, and so on. And A, you cannot have a 1 kilometer heat exchanger because it's not economical and you have no space. Therefore, you add the fin in order to do that, okay? Therefore, this is, again, the other side of the conduction that you have to learn, okay? We did a 2-3 problem. Therefore, try to understand physics behind that and try to understand how we develop the equation. You don't need to memorize it, but at long as you see, we wrote a simple energy balance for a control volume, conduction plus convection is equal to 0, okay? There is no energy storage capacity. Now let's do this problem together. If you would like to write a novel, or you would like to participate in police, read this problem. A person is found dead at 5 p.m. in a room. The temperature of his body is 20 degrees. The temperature of the body is measured to be 25. The room temperature is 20 degrees. That room is temperature 20 degrees, but the temperature of the body of that person is 25. And the heat transfer coefficient in the room is 8 watt square meters and Kelvin. The body can be considered as 30 centimeter diameter, in good shape. This is the diameter is, and 1.7 meter long cylinder. Could you tell me when that person was died? How we can solve this problem? You have seen a lot of movie in the TV, right? The detective goes there and says, well, he was dead almost 5 hours ago. Any idea, my friend?
Sir,
Yes, sir.
do we consider the temperature of the body at 37 degrees at first?
At first, yes, he was alive, my friend. He was alive.
That's what I'm saying. Like when he was alive, we consider 37 degrees.
That's
Okay.
right. Then he dropped dead. I do not know what happened to him, but dead. And then when they opened the room, they find his body's there. And that guy came here and said, oh, the temperature of his body is 25 degrees. What is the process happening now?
Well, we have the temperature difference between the body when it was found, when it was alive, and when it's found.
Okay, what can I do?
We have the heat transfer coefficient.
So what?
But it's not related to time,
it was 37, probably 5 hours ago. It was 35, 32, 30, 25. The time is changing. Forget about this guy. You get a coffee and they come, I don't know, you get it from Starbucks, okay? The temperature is around, I don't know, 50 degrees, 60 degrees, and you put it on your desk. And after 15 minutes, 20 minutes, 30 minutes, the temperature drops to room temperature. What process is taking place? The process here is losing heat to the environment. Therefore, you can assume that cup of coffee or this person has a certain energy in his body. And now it's placed in this room and slowly, slowly releasing this temperature to the environment. Therefore, if you look at this person, his temperature was 37 when he was alive, but he's dead. There is no internal anymore heat generation. It's slowly, slowly losing the heat, to the environment, okay, by convection. Therefore, now we are bringing a new topic. It's not anymore a steady state. The temperature of the body is changing. The temperature of the coffee is changing. Therefore, it's not anymore a steady state scenario. Now we are involving energy storage component. Therefore, here is, we call it transient. Therefore, so for the problem we did it was a steady state. But now it's transient, it means it's changing as a function of the time, okay? Transient, it means changing as a function of the time now. It's not anymore the temperature constant, no. The temperature of the body is changing from 37, 34, 33, all the way to 20. The objective of this chapter here is assess when the variation in the temperature in the body, for example, is negligible. For example, if I'm trying to solve a problem dealing with, let's say, a stainless steel, I can assume it's a high conductivity, therefore the temperature everywhere I can assume is the same, okay? This is, we assume the temperature distribution inside that system is negligible. Therefore the temperature at the surface is 60 degrees, the whole body is 60 degrees, okay? Therefore here we can assume, here is a temperature very nearly uniform in the time, okay? This is making a simplified assumption that, the body, now this object, whatever it is, the temperature everywhere is the same. This is an assumption we can make in some scenario, and it is acceptable. And then obtain analytical solution for transient one-dimensional conduction. We can apply to rectangular, transient, cylindrical, and spherical, and so on, using the method of separation variable. This is one scenario that we can assume the temperature everywhere the same. But sometimes we cannot make that assumption, and we have to come and try to solve the differential equation that we had. Now we cannot ignore dT over dt, variation of the temperature over the time, that we have to take consideration also that phenomenon and try to solve. Only we do it for one-dimensional because it's easier, because it's difficult to solve the differential equation, okay? Therefore, we do it transient, one-dimensional problem for this three type of system. Therefore, I'm sure you all know how to solve this separation variable. I'm sure you passed because you passed math 233, okay? Therefore, we use separation variable, but again, this is not math, this is your responsibility to know it, but we give you the solution. Solve the thermal transit conduction problem in large medium. When it's large medium, we can assume a heat transfer is one-dimensional, okay? For example, if I have a long cylinder, I can assume the heat transfer is only through the radius. Because since this is long, I can assume everywhere the temperature is the same. Therefore, we can apply that one for one-dimensional case and trying to find a procedure to solve that problem, find the temperature distribution inside the cylinder. Or if I have a wall and the temperature on both sides of the wall is changing, probably we can use that scenario, okay? Conduction solution for multi-layer. Again, here is the case that we have for one-dimensional, that I can apply for long cylinder, I can apply it for a long wall, but how about if I have a cup of coffee? It is not anymore long because I can lose energy from the top, I can lose energy from the side, okay? Therefore, it now become two-dimensional and sometimes three-dimensional. Therefore, we're trying to find a way to apply this one solution that we find for the one-dimensional, apply to the two-dimensional or three-dimensional, okay? Therefore, this is simplified version. Probably we can make an assumption most of the time. And if they cannot make that assumption, therefore I have to find a way to solve analytically for one-dimensional. Then if I find the solution for one-dimensional, I can use mathematical procedure. Again, you have seen it. Product of the solution, you have a solution for x direction. You can assume the same solution applied to y direction, and you multiply to find the two-dimensional, okay? We will go through this on step by step, okay? For example, the first assumption that we mentioned, we mentioned this one, okay? If I look at this is made of copper, I can assume this because of its high conductivity. I can assume the temperature everywhere inside the sphere, not on the surface, not only on the surface, but inside also everywhere is 70 degrees because it has high conductivity. As heat reach the surface, it can penetrate fast inside. Therefore, if I use an analogy, is here convective heat transfer come here and then go here. If I want to use it, I can use the analogy that you're coming to the downtown Montreal, very heavy traffic. When you get to the highway, you can go fast. Therefore, here is one resistance and here is another resistance. This resistance is much higher than here. Therefore, heat entered the surface. Therefore, from here on, there is no resistance and the heat can transfer fast. This is, I assume, everywhere in the cylinder, in this sphere, the temperature is 70 degrees. But I cannot use for that dead person over there, okay? Because here you have a high resistance. Probably in the surface, if you're trying to put this in your oven, when you're cooking, and the surface, the top is 110 degrees because it's in the oven. It takes some time, the energy transfer to the meat to get to the center. Therefore, that's again by itself is an art to design a stove, okay? When you're having a stove, that has been a lot of research, how to design it, create a convective radiation here that you don't burn it in the top. You would like to produce it to have a relation between convective heat transfer here and here. That's why they're asking you, what are you cooking? Therefore, because when you're setting up, you're trying to balance between this resistance here and this resistance here. Because here is very low conductivity. And therefore, by the time the temperature here become 100 degrees or 70 degrees, here probably is too much, okay? Therefore, now we have to consider where is the resistance. Here is here or here. And that's why we call it lump sum analysis. Lump sum parameter or lump system analysis here is, we assume there is no resistance here, okay? That we see this statement on and on and on, okay? Therefore, if I want to do it, look at here, imagine that you have, again, I'm trying to write a simple energy balance, okay? Keep in mind that I assume there is no conduction in the wall. There is no conduction in this ball. Temperature everywhere is the same, okay? Ignoring the conduction. You have convection and then some energy. Therefore, assume that you have this one at 70 degrees and you take it out and bring it to the room. From environment that everywhere is 70, you take it out and bring it outside in the room. The temperature of the room is 20 degrees. Therefore, this is slowly trying to lose heat to the environment. Therefore, it has a certain amount of energy. Now it's convecting to the environment. Therefore, we write this equation that we have. Heat transfer to the body during delta T. This is amount of the energy that either you're losing or gaining by convection. This is the amount of the energy, okay? Depending on the temperature. And then there's a change in the temperature of the sphere. It was 70 degrees, then becomes 69, then becomes 68, slowly drop. Therefore, it has an initial temperature of, let's say, T0, Ti, okay? The initial temperature is Ti. And slowly, for example, is cooling down, is losing the heat to the environment. The environment is T infinity. How? By convective heat transfer and depend on the area. Therefore, this is the amount of the heat losing to the environment. But how much energy it has is mass times Cp times dt, okay? Therefore, we are trying to write it down here. Therefore, we write here is, this is the amount of the energy transfer to the environment during that time. Could be 5 minutes, 10 minutes, 1 hour here. This is during that period of time. This dt represent the times. And then how much energy lose from the system is dependent on the mass of the system that have and the ball that we have, Cp, what was the material, and temperature drop of that system during the time, delta T. Temperature drop 10 degrees in 5 minutes. Therefore, this is the variation of the temperature of that mass, that assume that ball that we have over the time. If I arrange here, we know the mass is equal volume times density, and we can write the equation like this, okay? Therefore, now this your equation become this format. Again, here is variation of the temperature that you have, dT that you have here. Again, we are changing the variable because, again, I hope you feel comfortable here. Dt and here is the same, because if I take the derivative of this expression here, this is variable, remain dt, and this is constant. The derivative of the constant is equal to 0. Therefore, we are using a change of variable. Therefore, this, by assuming this dt here is this one, my equation that I had from here will end up like this. This over this that I have, h here, that area divided by rho Cp. Therefore, this is the differential equation. I just change it to this format. It's easy because now it's make it easy for me to take the derivative to the integral. Therefore, the integral of this one is become t log of t minus t infinity. Okay, am I correct? dt over this one, if I take the integral, become log ln of t minus tb, and here it's become this is constant and become t. And now we can calculate, and this become like this. Okay, therefore become log of this one and divide by this one. Therefore, here these are the initial condition that we have at the time equals 0. If we get this, if I take the integral of this, become integral of t between 0 and this one. At the time equals 0, the temperature here, it was Ti. Initially, it was a Ti. And then I can calculate the temperature at any time. Any question, please? Any question, please? I need a volunteer to say yes or no.
Yes, sir.
Therefore, what we did, we wrote a simple energy balance for the system. It was initial at a certain temperature. It loses heat by convective, and the temperature of that body will drop, and that become here, or increase, depending on what was the initial temperature, okay? If I take it from oven, the temperature would drop. If I put it from fridge, the temperature will increase. Therefore, the only way is by convection. Therefore, this is my differential equation I have. I only use change of the variable I take, and here is, I need an initial value. I know the temperature at the time equals 0. Initially, at the time equals 0, everywhere of this body, the temperature was Ti. When I solve this differential equation, this is the solution that I have. Keep in mind here, I assume lump system analysis. Please be familiar with this terminology, lump system analysis. What that means, it means I ignore the conduction through this material. When the temperature here becomes 65, everywhere the temperature is 65. Therefore, there is no resistance. Therefore, I ignore the conduction. That's the idea. Therefore, you will see this terminology a lot in your future job. Lump system analysis, it means I assume everywhere is the same temperature. By making that assumption, I'm ignoring the conduction. Therefore, I end up with this one. Heat transfer from the body is caused that the temperature of the body will drop or increase, depending on the environment. And I end up with this equation. Knowing this initial condition, I end up with this equation. Therefore, at this time, if I take it from somewhere, initial temperature, I put it in environment, the temperature is infinity. And now I can calculate the temperature as a function of the time. The temperature as a function of time, because I know the convectivity transfer coefficient, I know the area of the body, I know the density of the body, copper, water it is. This is the volume again, and this is Cp. Therefore, now we have an expression that I can easily apply to find out the temperature of the body. Again, and again. The temperature of the body everywhere is the same because I'm using the concept of lump system analysis. There is no conduction through the material. Everywhere the temperature is the same. Any question, please?
Sir, is the Cp specific heat?
Yes, sir.
Okay, perfect.
And here again, we can combine this, all of them together, and call them B. And B is defined as this one, okay? And for this, you can, the equation, you will see it is simplified because e to power B, and B, it just put all of this parameter together here. Is together, call it B, okay? And if you look at here, is the unit is 1/2, okay? And why over second? Why? Because H has joule per second. Therefore, that's the second here, okay? Therefore, now this is an equation that you can calculate the temperature in the body as a function of the time. It's not anymore a steady state. Now the temperature is changing. That's why I can calculate the temperature as a function of the time to do that. And this term, and when we start to have some idea and control, they call it the time constant. How the system behaves, the change time, they call it time constant of the system, okay? This term called time constant, okay? The B value called time constant. If you look at here, now you can see the effect of all this variable. As here, this represents that you have initially something, for example, in the fridge, is cold, and you bring it and place it in an environment is called T infinity. And the temperature of the body is slowly increase, depend on the time constant, okay? And as you can see, it's exponential, is increasing exponentially, okay? Therefore, it's increasing, and as the time constant increase, this value will increase. You can just, okay? This takes some longer time to do that. This takes shorter, and depend because here it represents there's much higher convective heat transfer. Therefore, that's slowly reach to the room temperature, okay? And as I mentioned, this called a time constant, and you can see the temperature variation is exponential, and right here it is e to power this one, and that shows the one. Okay, now let's go back to here. As we mentioned again, this is the rate of the convection. Therefore, you can not only you can calculate the temperature at any time, because you can put 1 second, 2 seconds, 5 minutes, 10 minutes, 1 hour, and you can calculate the T. And from there, you can calculate how much energy at any time, at any moment transferring. Because here you calculate the temperature, you put the equation, said at 10 minutes, this is the amount of the convective heat transfer to the environment, okay? And also you can calculate how much energy lost from the system, because when you calculate T, again, you can calculate, put this equation and say, okay, this is the amount of the energy at this moment it exists in the system, okay? Because temperature was 37, now dropped to 35. Therefore, this is still the remaining energy in the system, okay? Therefore, these are expression. Now you can see this, the temperature now is changing as a function of the time. It's not anymore a steady state. It's changing as a function of the time, okay? The maximum, when it's maximum, it means this is the time reach steady state, okay? When it reached T infinity here, from here, reach to this temperature, this is the maximum temperature, the energy losses. Initially, the system was at this temperature, now is at this temperature. This is the maximum energy transfer. And that's exactly the meaning of this one, okay? The maximum heat transfer between the body and so on, okay? Therefore now, this is, if you would like to visualize what happened here is, initially we had a time equal 0 everywhere. The temperature was Ti. Now we took it outside, either could be from oven or could be fridge, and put it in the environment, that the environment temperature was T infinity. And that at that room, the convective heat transfer was H. After a long period of time, T become infinity. Therefore, now everywhere is T infinity, okay? Therefore, we are trying to find the process from here to here. And that's why exactly we can calculate any time from T0 to infinity at any time, the temperature of the system, how much energy has been transferred. And here is the maximum. Initially it was here and here. This is the maximum energy exchange. The maximum energy exchange is equal to MCP because from initial to here, this is how much energy transferred from system to the environment. Any question, please? Therefore, we are slowly, we're trying to integrate the time because so far we assume everything is the state, but in reality, that's not the case. Any question?
So basically, if we take that for the case of the body, we need the CP of the body, of a human body.
Okay,
Per se.
let me go back. Okay, now let's.
But it would be different because we're looking at a case where the temperature increases. So if
It doesn't matter. Increase or decrease doesn't matter because that expression
Mhm.
we wrote in general term. Ti
Yeah.
be more T infinity more. This give you energy given to the system or energy taken from the system.
Yeah.
Okay? Now let me just go. We come back to that question that you raised. That's correct. Okay.
Okay.
Again, here we are looking about this scenario. And we mentioned it's solid, we have body, conduction is coming here. And now if you go back and look at this expression that you have this system B here that has nothing to do with the conduction. Has nothing to do with the conduction because we ignore the conduction. We said there's no conduction. But in reality, sometimes we cannot make that assumption. Therefore, we are trying to come when we can use this concept, when we cannot use. When you can use, assume the flow is laminar, when the flow is turbulent. Therefore, we have to find an indicator to be able to distinguish when I can make that assumption. I can make this assumption, but I have to have some criteria. Therefore, we have a number called BO number. BO number. What this BO number represents, if you look at carefully, it considers the ratio of conduction inside the system. We have a resistance here from, let's say, from here to the center, a resistant conduction, because we can assume it's uniform everywhere. There's a resistance to conduction that's dependent on the conductivity of the material and radius in this case. And also I have a resistance from here is to the convection. Okay, we have a resistance here to convection, 1 over h, and I have a resistance inside the body is L over K. Okay, L could be radius and so on. Therefore, we are trying to convert these two resistance in the conduction to resistance to the convection. If this ratio is less than 0.1, we can assume LOM system analysis. Therefore, now you have a criteria to see if can I make this assumption or not. And that criteria, we call it the BO number. Remember Reynolds number? You can assume flow is laminar if inside the pipe is less than 2000. If it's more than 2000, it's turbulent. Here is another criteria. I have to use this index. I call it the BO number. And based on that one, if it's less than 0.1, I can use that equation that I learned, okay? Now let's go and look at here. Look at here, when the convection coefficient is high and K is low, large temperature difference occur. If I assume a high heat transfer coefficient here, when I look at the high heat transfer coefficient, it means the resistance is what? Less, very small. But if I assume a low conductivity, if I go back here, if I assume high resistance, it means this resistance is very small. If I assume a low conductivity, it means this high. Therefore, in this case, I have a resistance here, and I have a temperature variation to the system. At the center is 130, but as I go slowly to the surface, the temperature change. Therefore, you can see I have some temperature variation. In this indication, it means I cannot assume lump system analysis, okay? We can use the same analogy for the car and both, as I mentioned, again, transportation, okay? If you bring 5,000 people and then you go to the ocean and then you would like to take them to the island and you have traffic jam, therefore this you cannot assume the velocity here. There is a traffic jam, there is a temperature drop, here is that you have a traffic, okay, if you would like to use the analogy. Okay, again, as I mentioned, those analogy, you can use it, apply to voltage, you can apply to heat transfer, you apply to transportation, you can apply to even economy, inflation that we are talking, right? Therefore, that we can use this concept again. Let me go back to the person dead. Now you tell me what should I do?
We need mass of the body, the weight.
No,
We need CP.
Okay. Do you have a textbook in your desk, sir?
PDF, I have to open it.
Okay, open your textbook. And this is the best time to use it. And go all to the back of the textbook. And you can see there's a table, give all the physical property. And I believe there's one table here. We assume, again, there's an assumption that we can assume that 90% of the body is water. Therefore, you can assume this person, his meat is made of water, and take the physical property of the water, okay? Therefore, you look at there, you can see for water, you can assume, you can measure, you can see the value for density, you can see the value for the specific heat, you can conductivity, and so on, okay? Therefore, look at your table and your textbook, and at the end, let me see, use my textbook here. I believe it's table A9, I'm not sure. It mentioned table A9, table ABC A9 at the end of the book, and mention property of saturated water. And if you look at that, there is a temperature here and give you different value. They give you the density, they give you the enthalpy, they give you specific heat, they give you conductivity, and so on, okay? Therefore, this is, you can use it, end of your textbook. Now, from now on, all the physical property can be given from that part. Therefore, that way place, we go there. As I mentioned, yes, sir.
So we should consider the CP vapor.
You can assume it's
Right.
water. You can assume it's water. Okay.
Okay, liquid.
I believe so, liquid, I believe so. I can assume that one. The property of water, and you can use table A9 to find all the physical property. I give you 2 minutes to see what we can do. Take some water. Okay. Therefore, you have all those physical property. You have an equation, and you mentioned, well, let me assume is I can ignore the resistance inside, and then you calculate here. And now, since the body changed from 37 to 25, therefore the physical property, if you look at table 8.9, the physical property will change. Therefore, you take the average temperature. Initially, it was 35, 37, now it's 25. Therefore, you can look at that table and find the physical property at that time. Therefore, the conductivity is 0.617. I do not know if I need conductivity. The density is 996. And also you can calculate the CP and that value. Therefore, these are the value at temperature of 31. Then I go and calculate, and now I know that this guy was in good shape because the diameter is 30 centimeter. and 1.7 meters. Therefore, I can calculate I consider him as a cylinder. Okay, a cylinder, 1.7. I have the diameter, therefore I can calculate the surface area, and I can also calculate the volume. Any question? Therefore, we can calculate. Are you done this slide?
Yeah.
Good. Therefore, these are the information we get it from the table 8A9. Now we start to do the solution. Therefore, I can calculate the B because this was a time constant. In order to do that, I know the H, I know the rho, I know the CP. Is missing is A, as I mentioned, I assume is a cylinder. Therefore, the surface area that he's losing heat to the environment. Therefore, these are we calculate here. We calculate the area, volume, and this gave me the value here I have here. Therefore, here I know the value of the B I calculate. I know the temperature of the body with the time we find. It was 25. Initially, it was at 37 degrees, and the room air temperature was 20. Therefore, that shows this guy almost that 12 hours ago. Any question now? Again, these are something that you can calculate the volume on A and so on. They didn't write it step by step. It's a cylinder. The surface area is pi dl. Volume is pi square, pi r square times L. This is the volume, okay? Therefore, they can summarize and find A over V is equal to this number. Therefore, if you calculate here, you can see now I have an expression. I can look at the temperature variation as a function of time. And here it was initially at 37, dropped to 25, and this took almost 12 hours. But I made an assumption. What assumption I made?
It's lump sum.
What that means? I ignore the conduction through his body, right? I assume the temperature of the surface is the same as temperature in middle of his body, okay? Therefore, let me go back and check if that was the right assumption. It means let me go back here. Please just bear with me. Let me verify if my assumption was correct. That this the BO number, if it's less than 1, I can use that expression. BO number, if it's less than 0.1, I can make that assumption. And BO number is LC. LC, it means V over A. We call it characteristic length. Please be familiar with this terminology. We use this terminology, characteristic length, in the future. Characteristic length. It means the ratio, the volume divided by area, we call it characteristic length, okay? Therefore, this is the term we are using here. Therefore, I know the volume, I know the area, I can divide it from the characteristic length, I have found it. I know the conductivity of the water, because we look at A, table 9.A, 8.9, okay? I know also the convectivity transfer, therefore I can calculate my BO number. Therefore, if I go back here, this is the characteristic length I get at here, okay? It's by dividing volume over A, okay? This is the characteristic length. Therefore, if I use this one here, I can see my BO number is more than, is 0.1, 8.9. That shows, indicate that my assumption was not correct and this answer is not correct, okay? Therefore, now we have an indicator, and that's, we call it BO number, that we know when we can use this equation. The only time I can use this equation, if the BO number is less than 0.1, but here is more than 0.1. Therefore, this, my procedure is not correct, therefore this answer probably is not correct, okay? Therefore, now we have an indicator, we can say when I can make that assumption, when I cannot make that assumption. Therefore, this shows that I cannot make that assumption. the question here is how I'm going to solve that problem. Please write it down, and if you have, let me know when it's done, that I can continue the lecture.
Sir, you were saying we should find out the BI number first, then choose which method to use?
That's correct.
Okay.
Therefore, always you have, first thing you have to do, you have now two solutions. One solution we discuss it now, and one solution we are going to show you shortly. Now, this simplified equation, this is a very simple way of doing it because we make an assumption and therefore we end up with very nice equation here. But this equation is only applicable when BO number is less than 1, then less than 0.1. But if the BO number is not less than 0.1, therefore I have to find another way of solving. It means I cannot assume that I can ignore the conduction to the solid material. Therefore, the resistance inside by conduction is the same level as resistance by convection. Please let me know whenever you finish this slide. As you write it down, if you have any question, please do ask me, okay? Therefore, this number comes from there is this one here, okay? This number. This is, we call it characteristic length, V over A. V over A, this one here. Therefore, this is, we got the answer that this person died almost 12 hours ago, but we go and verify if my solution is correct, and that's the only way I calculate the BO number, and the BO number I find is 0.89, that indicate this is not a good, the assumption that we made is not correct, okay? And if you look at also the surface area here, we calculate it from the body and also from the top and bottom, because this is cylinder from his feet and from his head top here, okay? But here we assume he is a cylinder at that time. Any other question, please? Okay, let me move to next slide. 1, 2, 3. Now let's look at this problem. Read this problem because I would like to show you the solution, but first you have to see what is the application that you have much better understanding of the problem. Let me go too fast because then we come back later on. Okay, now let's assume that you cannot ignore the conduction of the problem. Look at this system here. If I look at this system, can I ignore the conduction or I cannot ignore the conduction? Look at here, I have a system. At the beginning, the temperature everywhere is like this. As we expose this system to outside, the temperature outside and temperature slowly increase, and finally this was the case, okay? Therefore here it was at initial temperature. This was a time equal 0. When we expose them to the environment, the temperature slowly increase. This, in this thickness, the temperature here. And as the time passed, the temperature will increase like this, okay? And then become here and become like here. Look at here, the time equals 0. The temperature in this side is almost Ti. In this point here is Ti, but at the center is still Ti, okay? But here slowly the temperature drop here. After in time infinity, we have temperature everywhere here. Therefore, here is a steady state. Therefore, you can see there is a resistance to the heat transfer to the wall. Therefore, we cannot assume the temperature everywhere is the same, okay? Before it was here, it was the temperature here, everywhere it was like this. But now we can see there's a profile of the temperature inside the body. Here is the time initial, the Ti. We expose it to an environment, the temperature is T infinity. And this line represents the temperature distribution in the body as a function of the time. Here the time equals 0, here is the T infinity. Ti everywhere the temperature was Ti. After a long period of time, everywhere the temperature here. But in between, we have a temperature profile inside the body. It's symmetric because both sides are exposed to the same environment. This side is infinity, this side is infinity. Here is H, therefore this is a symmetric system. But the only thing we're trying to show, look at here, there's a temperature profile inside the body. Now, we're trying to find a solution for 3 different geometry again. Again, we're talking solid material, could be a Cartesian coordinate, rectangular. Again, here we make an assumption that the whole system is in the same environment. This side of the wall exposed to infinity, and the same here. We have a cylindrical and we have a spherical. We're trying to find a procedure to be able to find the temperature distribution inside the body as a function of the time, okay? As a function of time. Here is shows the time. Look at here, T0, this T1, T2, and so on. Let's look at a rectangular system because it's easier, X and Y easier to look at. I assume one-dimensional. This is the term, conduction. Remember equation that we have in chapter 2. We had this one, we had another term, it was heat generation inside, we ignore it, and we assume is transient, therefore this term remain here. Okay, this term remain here. Therefore, this is conduction through the wall. If you go back chapter 2, you remember this one we developed. And here represent variation of the temperature in this body as a function of time. Temperature at different location, temperature as a function of time. Therefore, this is a partial differential equation. We have variable x and variable time. Therefore, we have to solve this differential equation knowing 2 boundary condition, 2, and on 1 initial condition, okay? I'm sure you did it as part of math 232. But the way we do it here is we're trying to separate the variable, okay? Therefore, what are the boundary conditions that we are trying to solve? As I mentioned, 2 boundary conditions. We have a x equals 0 and x equal L, and the t at equals 0. These are boundary conditions. Therefore, we can assume 2 cases that the system at the center, because as I mentioned, the boundary condition here is the same as here. Therefore, there is no heat transfer in the center line. That's represent there is no heat transfer at the center line. At x equals 0, there is no heat transfer. Therefore, it means adiabatic. Why? Because the temperature here is the same as temperature here. Therefore, the temperature is the same, there is no heat conduction. And also assume the surface in this side and this side is the heat transfer is by convection. Therefore, at this point, x equal L, at this point, the conduction is equal to convection. And that's exactly the same, okay? It's mentioned that there is no, the system is symmetric, there's no heat transfer at the center, and also the surface, the only heat transfer is by convection. Therefore, here is convection, and exactly is the same as the amount of the heat is by conduction, okay? And then we come to the initial condition. I assume that this system initially it was everywhere, irrelevant of x, the temperature was Ti. Assume that was in the fridge for 1 week, and you take it out. Therefore, the temperature, you can assume temperature everywhere is Ti. Now, we have to solve this differential equation, partial differential equation, because it's time function and the x, considering these 2 boundary conditions. I'm not going to do it, but I'm going to go through it quickly. This is a math. You had it in E233, and therefore the best way to do it is trying to normalize it or using a dimensionless, because you're trying to solve this differential equation can be applied to any type of x and thickness and so on. Therefore, we do that, and we sort of normalize it, and this equation that you had from here, by change of the variable, it's become this equation, this is exactly this equation, now is dimensionless. Therefore, it's not depend what the temperature is, 20 degrees, 40 degrees. Therefore, this is applicable to a certain boundary condition, but when you solve this equation by normalizing it, you can apply it to any boundary condition and initial time. Therefore, this equation is exactly this. By change of the variable, x is divided by here, and theta is we define here. This is 9-dimensional. This is temperature divided by temperature. There's no unit. X divided by L, there's no unit. It's trying to solve this differential equation. This differential equation, this boundary condition will change to this boundary condition. This boundary condition change to this one. That initial time to change to this one. Therefore, what we have done with change of the variable, by change of the variable, we make this equation dimensionless that you can apply for any sort of system, because it's not anymore the function of 5 centimeter, 10 centimeter. The solution that you find to this differential equation here, you can apply it to any boundary condition, okay? That's the idea we do it in mathematics, okay? Now you have this differential equation, trying to solve it. Therefore now is this dimensionless, and I believe the way you did it, I didn't take EMAT 233, is become this is dimensionless, this dimensionless. Therefore you can do the separation and you find the answer to this one and answer to this one, and then multiply them together. Therefore this one you have done it. Again, you end up by doing it, you will see by non-dimensionalizing it here, and here, you will see there is a new variable that comes out, and the new variable, call it a Fourier number. Therefore, the temperature here, let me choose here, you had the BU number before, you have seen it before, we non-dimensionalize it, we have this one, and by doing this non-dimensionalize it, you find that another dimensionless number. This is another dimensionless, this is also non-dimensionless here. You call it Fourier number. Therefore, now you have the differential equation, and you're trying to solve this one based on this boundary condition that you have. But by doing non-dimensionalization, you will end up to have 2 other dimensionless numbers. And if you look at what is the physical meaning, again, we have to go back. As I mentioned, we look at the Reynolds number. Reynolds number was representing of 2 forces, inertial force and viscous force. Therefore, there are 2 functions. Fluid wants to go through the pipe, but viscosity was inventing. We have BU number, again, is ratio of 2 forces. You have convective and you have conduction. Therefore, it's trying to compare which one is dominating the system. And when we come to the Fourier, again, trying to understand the physical meaning of Fourier, is representing the rate at conduction to the rate of which energy is stored. Energy passed through the wall. Now, what those conduction passing through the wall, a portion will be stored inside the material. Therefore, that's called Fourier number. In some textbooks, they show it by F, and some textbooks they show it by tau. Therefore, that's this is, sometimes they show it with F, sometimes they show it with tau, okay? Therefore, now we have another terminology. Therefore, the rate of which heat conducted through the body and the rate at stored in the slide, okay? Therefore, this is the have. If you would like to visualize it, I'm sure you remember this in your building science textbook. There is some conduction coming to the wall. Out of those conduction, all of them will not go here. That's only in case of a steady state. But then, and when you consider transient, portion of that energy will store inside the wall, okay? Therefore, this plus this become this. And Fourier number shows what portion conducted through the wall and for what portion is stored in the wall, okay? That's the meaning of the Fourier number. Therefore, here shows how much energy will store inside the wall and is slowly going to release later on. What portion of them pass immediately, okay? Therefore, that's also Fourier number. Now, let's go back to the differential equation that we were trying to solve. If you remember, when we, in general term, when we are writing here, general term, we have one function here and another function here. And we try to use this approach, we assume is equal constant, and to try to solve this differential equation, and then we find an expression here. Therefore, please go through it. This is, you had it during the math. This is the general solution to that problem for X function, and this is the general solution for time function, T function, and your general solution for a theta is a multiplication of this one and this one. Now, x is again, we define dimensionless. Lambda, we're trying to find out here what it is. And lambda is equal to that number that you have is, we assume this is equal constant, and they're trying to solve the expression that you have, okay? Therefore, you assume this only function of x, this function of the time, you assume is equal lambda squared, and lambda squared, you're trying to solve equation for this x function, you're trying to solve the for t function here, and then you multiply these two numbers together, answer, to find the answer for the theta, okay? This is, you have seen it 223, okay? And this is general form of equation. Now you have two boundary conditions we're trying to apply. I'm not going to step by step, please read it, and you, as you can see, this becomes very complicated differential equation that you have to solve. When you solve it, you will end up this one. If you solve it for wall, okay, by the procedure, as I mentioned, separation of the variable, non-dimensionalize it, separation of variable, and so on, you will find this function shows the temperature distribution in the wall. Okay, theta, as I mentioned, is dimensionless temperature. It means T minus T infinity divided Ti over T infinity. This is theta that we have here. Okay, let me go back, remind you what is the theta. When we non-dimensionalize it, we define theta as this one. Okay, this was the way the temperature at any point and any time, because now we have two variables, time and position. This was the temp infinity where we are exposing, and Ti, it was the initial temperature. Therefore, this theta that you see, that equation is this ratio, okay? Therefore, here now you have an expression. You have an expression here that they gave you the temperature as a function of the time, okay? Here at any point and any time. Look at here that you have this one, x, and you have t. Therefore, this expression gave you the time at any time and position, okay? And then you have the same solution when we solve it for cylindrical. Again, we're not going to do it. As you can see now, you have seen the J function that you have here, okay? These are Bessel function. Bessel function, okay? These are Bessel function, call it, that we have it, okay? Therefore, you have to solve first the Bessel function to find out this lambda here, and then place it here to solve it. And this goes from n1 to n infinity, okay? This is a math problem, okay? Therefore, there is a way to solve that differential equation and get this answer. But the question as engineer is extremely difficult every time. You can't first solve the Bessel function to find this eigenvalue and put this eigenvalue n1 to nn to solve this one to find the theta. Therefore, somebody has done this work and they put this one as a plot. Just go to the plot here. For example, if you look at for the wall, they solved that differential equation, and you can see this gave you this axis and gave you the temperature distribution, okay? The temperature distribution here is T0. It means at temperature at the center. It's not at any point. Temperature at the center of that wall here. Temperature at the center of the wall here at this point. Yeah. And T infinity is the temperature of outdoor environment. Remember, again, we are considering a symmetric condition. It means the temperature outside here is the same as here. Heat transfer here is the same as here. And this, if you find here, gave you the temperature at the center, right at the center here. Therefore, this graph gave you a temperature at the center only. How you can calculate it? You calculate the BO number. Therefore, you have the BO number here is K, L, H. Therefore, you know the thickness of the wall, convective heat transfer, conduction. Therefore, the BA. Therefore, these lines represent here is the BO number. This line represents the BO number, okay? From 0.05 all the way to 100. And the other function that you need, this is, as I mentioned, is Fourier number. Remember, Fourier number is another index. I mentioned it. I repeat it again. Shows the percentage of energy conduct to percent of the energy stored. Therefore, here is a function of the time. And alpha is thermal diffusivity. This is the physical property of the material that you can find it from the table at the end of the book. If it's water, you know the thermal diffusivity, okay? And L is the thickness. Therefore, you calculate the Fourier number, you calculate the BO number, you go up here, wherever it is, and you come here, you find 1 point, and from here, you find the temperature at the center, okay? Therefore, this show you that expression that you have here. Let me go back again. Therefore, here, again, this is rather than sitting small. Yes, sir.
On the graph, it's showing theta 0, not t0. So we have to know theta 0 to find the t in the middle.
It doesn't show the theta 0. It shows you t0 minus the infinity. Let me go back again. This graph shows theta 0. The definition of theta 0, it means t0 minus the infinity. It means that this value that you read here is the ratio. T0,
okay,
temperature at the center, minus T infinity divided Ti minus T infinity. Okay?
Okay.
This is the definition of theta 0. Theta 0.
Yeah.
Okay? Now,
Okay. So from that, we find T0.
Yeah, you find
Okay.
T0. Now, therefore, but this expression gave you the temperature at any point that you would like. Therefore, somebody plot this curve and for you. But even for this is for general case. But again, we are coming and making it a little bit easier. And if Fourier number, this tau, is more than 0.2, that equation that you had here, can be simplified to this equation. Okay? And this is a scenario that you can use. And there is a table in your textbook. They gave you the value of lambda. Therefore, you apply your number that you find, you go into the table, you find the lambda here, and this gives you an analytical solution to calculate the temperature at every point, at any time, at any point, at any point, and any time. This expression here, my friend, this expression here for wall, for cylinder, for a sphere, only applicable if your Fourier number is more than 0.2. Therefore, if less than 0.2, you cannot 0.2, you cannot apply here. Therefore, this is for special cases, okay? This is the temperature at any point. But these three equations here, again, give you the temperature at the center. Okay, I'm showing you the graph, and I'm also showing you some simplified equation. Therefore, if Fourier number is more than 0.2, you can apply this expression here to calculate the temperature center, center, center. And you can apply this equation to find the temperature at any point as a function of the time, okay? Just in general information, okay? Therefore, rather than using this expression, is very complicated from 1 to infinity and so on. Therefore, this is simplified for case this. Notice if theta is more than, Fourier number is more than 0.2, you can ignore the rest of the term and only consider the first term. You don't consider lambda 2, lambda 3, lambda 4, lambda 5, and so on, okay? And these are probably some of the equations that you can use it, solving some problem, okay? Because it's only take the first eigenvalue. And there's a table in your textbook, they gave you this value for a given BO number. Check, I forgot the number of the equation, okay? Let me go back here. But also in your textbook, you have 3 set of graphs for rectangular walls, for cylindrical and spherical. And for each case, there are 3 graphs. This graph gave you the temperature at the center of the wall. As I mentioned here, is T0. If you would like to know the temperature in other point, you can apply this graph. This is A, graph A here, and this graph B. Graph B show you the temperature at any point that you would like to have. Is X or L, X 0.2, 0.4, point this, and so on. Therefore, here is give you at any point that you would like on the wall. Okay? But here you have the BO number and you find out, but in order to use this graph, you have to know the temperature at the center. Therefore, you have to first use the table A to find the temperature at the center, and then you come here to calculate the temperature at any point that you would like to do that, okay? I will stop here because I would like first make sure that you really understand. Do you have any question? Then I will continue next lecture for the rest. Any question? Therefore, is the basic here is here. The basic started from here, my friend, okay? From here. That we go back to chapter 2, and this chapter 2 shows the conduction through the wall. There is no internal heat generation. We have conduction, and then we have a storage. We have to solve this differential equation. To solve this differential equation, we need two boundary conditions, because this is symmetric. We assume there is no heat transfer in the center, and in the surface, energy is by conduction and convection. And we know that at the time equals 0 here, we have to solve this differential equation. This is the math part. Again, it's worth, if you spend 5-10 minutes, look at your textbook to find how to solve this differential equation. We call it separation of variable. We normalize it. This part becomes independent. This becomes independent of the units. We solve for x. We find a solution. We find for t. We find a solution. And we multiply them. And that becomes our general solution. And that's exactly the way it's done. Okay? And that the way exactly we done. We separate value. This part only function of x. This part only function of the t. We separate them. This is equal constant because it's not units. Therefore, we assume this is lambda 2, lambda or minus lambda square, and then we solve this one and we solve this one. Okay, and then we find the solution and we multiply them. Again, this is math. Please go through it. I will be very happy to explain it to you, but look at the textbook to remember your math 232. Okay, and then I mentioned here this is a general solution. You can do it. You can find this general solution. For example, this is for the case of the wall. You can see from n1 to n infinity. Therefore, you have to solve and find the eigenvalue, the lambda here, lambda 1, lambda 2, lambda 3, lambda 4. This is not possible. Therefore, if we make an assumption for the cases, the Fourier number is more than 0.2, that equation can be simplified here. Only we have one term, the first term, not the second term. No, only we take one term. And we can find this lambda in your textbook is given you as a function of the Beer number. If you know the Beer number, you can find the lambda one, and this it gives you the temperature distribution inside the wall. It gave you lambda and A1. Therefore, you all know this one and this one, and you can solve it as a function of the position and as a function of the time. The same thing for cylinder, the same thing for a spherical coordinate. Okay. And again, for this is the general solution. The general solution from 0.05 all the way to 100. It means if it's more than 0.2, it means you're solving this area that you can apply here. Okay, this apply from 0.2 here. You can apply that equation. This will give you the temperature at the center of the wall. Again, remember, give you at the center of the wall. If you want the temperature at any point at the surface or any point, you can use table 4b. Therefore, now you have two solutions. One figures and one analytical equation. Please read it, and if you have any question, just let me know that I can help you to do that, okay? And I mentioned, please, he sent you a sort of, most of you guys gone already. He sent you an email, he gave you the Dropbox. Please make sure that you drop your assignment, your project before class, because he's going to remove the Dropbox after 3 o'clock, okay? If it's after that, this is your problem. He sent you and check it before that. Please do not come with any excuse at the last moment. You were not able to do that. Please check and reply to his email if you have any problem, okay? I'm here for the next 10 minutes. If you have any question, please do not hesitate to ask me. Otherwise, have a nice evening. Still, there is sunshine outside.
Sir, I have a question.
Yes, sir.
For the equations in the exam, are we going to be asked to solve these equations to come up with the last formulas?
No, this is not the mathematics. Therefore, believe this is not my problem. My problem here is I'm interested to physics of the problem at that one. Okay.
Okay.
We're not going to ask you to solve the differential equation, but you're a fourth-year student. At least
Yeah.
I would like to encourage you to look at to see how has been done. Your engineer,
Yeah, of course. Yeah.
you understand has been done. Okay, that's part. I'm not going to ask you to solve differential equation. Yes,
Okay.
in some cases I solve differential equation, but simplified that's related to your chapter 2 and 3. Okay.
Boundary conditions.
Boundary
Yeah. Okay.
condition. One dimension steady state scenario, not transient. A steady state probably we will be asked to solve one differential equation.
Okay. Perfect. Thank you so much.
No problem there. Any other
Sir,
question? Yes,
Sir,
sir.
I have a question about the graph actually that's on the screen right now. Is that supposed to be in
Yes,
the
yes.
textbook?
It is in textbook, yes. If you look at chapter 3, there are, I believe, to figure, let me see, I believe it was 3.7. I don't know the new version. In your textbook, it is in your textbook, chapter 3. No, we are chapter 4, I'm sorry. We are chapter 4. It is section 4.3, and you will have it. It's for a slab. It is in figure 4, chapter 4. It's called 417, 418, and 419. I do not know in the new text version, but the version 5th I have is 4.17, 4.18, 4.19. And here is the textbook. I don't know if you can see it.
No, I can't. Sorry.
I'm sorry. It's in your textbook. Believe me, it is in textbook. You have this one, and you have. Let me come back here. You have this graph. Call it the Hazel chart. Remember this term, Hazel chart? This is very famous. And you have this one, B, and you have another one, C, that give you Q, okay? Therefore, you have for a rectangular, you have A, B, and C, temperature at the center, temperature at any point, and how much energy has been transferred, that I'm going to cover next lecture. You have also one chart, one figures also for the cylindrical, again, temperature at the center, at any surface, at any point for heat transfer. You will see it in your textbook. If you have, it's in section 4.3, I believe.
All right, I'll go looking. Thanks.
Okay. Yeah. You have it in 4.2. Yes, in section 4.2. You have it. Okay. And you have also, please remember, the table 4.2. Table 4.2 gives you this value for lambda and so on, okay? When you're trying to solve this one, when you're assuming here, all the value for A1 and lambda 1 here, it comes from table 4.2. Therefore, if you know the BU number, you go calculate BU number and then look at the table 4.2, and the table 4.2 give you the value of A1 and lambda 1. If you have this one, A1 and lambda 1, you can solve this one as a function of the position and time and calculate the temperature at any point that you would like to do that, okay? Therefore, this, I have to write also here is lambda 1 and A1 comes from table 4.2, okay? Any other question?
Sorry, can I show you the equation I have for the ground balance for the project?
Yeah, of course you can. Let me just first share my screen with you, sir.
I don't think it's not on my computer. It's on actually handwritten.
Let me okay, show it to me if I can see it, sir.
Okay, I'll show just my. I don't know if I share my video. Can you see or?
If the share, the only thing you have to put on the computer. Here I can see you, your hat. I can see your hand. I can see the paper.
Oh,
but
can you see the handwritten there?
At this moment, I cannot see anything, sir.
No, okay. Well, oh, sorry. Yeah.
What is the question? What is the question?
Oh, actually, can I send it to you by email?
What is the question, sir?
But it's just because I wrote the balance for the ground and for the floor, and at the floor you have convection to from the surface, and you also have conduction from the material from the floor, but you also have, and you have to balance with the
no, you're right. All the energy go to that point is equal 0.
yeah, so all the energy meaning like the solar radiation from the window,
all the energy go to that point is equal 0. Therefore, if this is the surface of your floor, let me see where I can put this wall here. Okay, this is the surface of the floor here. Therefore, you write energy for this one. You have conduction to the ground, to the soil, and you have convection to the room air, and you have some solar radiation comes to that one. All of them to this one equals 0. Therefore, become K of the soil times temperature T floor minus T at 5 meter down, divided by 5 meter, plus heat transfer coefficient, convective heat transfer between room air and the floor, plus Q is coming to that point. How much Q comes is equal solar energy through that window times the area of the window times tau times alpha T. Remember, the area now is different. When you are writing for conduction through the floor, the area of the floor is the total area of the room. All of you pay attention, please. When you are writing convective heat transfer, the whole area of the floor you have to consider. When you're considering the energy comes through the window, the area is the area of the window, because that's amount of the energy comes to the room. That's Q of energy comes to that room. And that's the equation for the floor. Therefore, you write energy go to that point equals 0. Convective, conduction, and solar radiation. Summation is equal 0. Did I answer your point, sir?
Yes, thank you.
No problem. Any other question?
Sir, for the floor question, do we need to include the application of the shape factors?
I have no idea why shape factor. Why your shape factor? Because you're writing in numerical, my friend. You know the resistance to the soil.
Yes.
You know the resistance to the convection. Why you would like to consider shape factor? Why? Because you have this, you have the floor, and conduction comes through the floor soil. Therefore, you have K thickness of the earth, temperature difference times the area of the floor.
Okay. Yeah, I see.
Okay. Therefore, you have a resistance to the conduction, a resistance to the convective, and you have some source energy comes to that point. Summation of this three has to be equal 0.
Yes. Thank you.
Again, I mentioned you do not need to use any of the shape factor. You do not need to consider cooling load factor. You do not know. No, you just write a simple energy balance for every point. Okay? Because this is a common mistake every year. Some people, they use solar factor. Why you are using? Because we already have the number. We are writing energy balance for every point. Energy balance for every point. What question? Any other question? Please start to do that. I will send you the solution to assignment number 1 and assignment number 2. That because I know you had the first set of tutorial last week. I hope by now you have done. And if you have any question, please do not hesitate to contact me or TA. Please follow me as we progress slowly. Okay? Don't fall too far behind. Any other question? Again, there is no question. Thank you very much for your time. Go outside, not too far, stay outside, take some fresh air. So there's nice solar energy. All the best. Take care.